Today, as we talked about last year during the previous lecture, we will continue exploring other types of robots. So we mainly focused on robot arms, if you remember. Last week of the previous year, we talked about flying robots, drones. And today we'll see, again, like kinematics and all the modeling work for other types of robots, more specifically for robots with wheels, like ground robots that move around with wheels. We'll talk a little bit about wheels, what types of wheels we have and what kind of wheeled robots we have, combining them. How do these robots move around so that we start developing basically the forward and inverse kinematics for this kind of robots. And we will also present the dynamic modeling side so that later on we can talk about control if we want. We will not go into control specifically, but it's pretty straightforward from what we've seen so far to, if we have the dynamic model, to also control them. So basically we're still working on this grand scheme, so we're talking still about this great robots side here. All right, but before we talk about all these things, why are we even talking about wheeled robots? What are the advantages they bring over robot arms or flying robots that we've seen so far? What kind of applications can we use them for?
They can cover a big area quickly.
A big area, what?
They can move in a big area rather quickly.
Oh, okay. Quicker than drones or not? Sorry. Quicker than drones or not?
Slower than drones.
Slower than drones. So what would be the benefit over drones then?
They're easy to control.
Easy to control, all right. Because they're more stable. So that's part of the easier to control part. Yes?
Because with drones we can have heavy payload.
Yeah, so the payload can be higher than with drones. With drones we can carry things as well, but we're limited. With mobile robots we're all limited as well to some extent, but yeah, the payload is higher, so yeah. Okay. Other considerations? Where are we using currently mobile robots, wheeled robots? Factories, but for what? Warehouses, okay. For, I don't know. Yeah, moving things around, logistics, I don't know, storing things, retrieving things, taking things to places. Like there is this large parcel sorting and sorting facilities where they use like, I don't know, thousands of them coordinated and so on. Sorry? And exploration a lot, yeah. I know, especially space exploration on other planets. It's basically wheeled robots. You should have come up with this one. Yes, there are a lot of nice applications, and the reason why we use them, indeed, they're more stable in the sense that, you know, in order to keep them from, you know, where we don't have to consume power, contrary to drones, where we constantly have to have the wheel spinning, the blade spinning so that they are hovering, right? So we constantly consume power, while with mobile robots, when we don't do anything, we basically don't consume any power. And the advantage over robot arms is like, yeah, they can move around and they can deliver things, while robot arms are limited in their workspace. All right. To move robots with wheels, we need wheels. And there are different types of wheels. We're not going to go too much into details here, but yeah, we'll see basically some basic differences. We have what we call the fixed wheel, in the sense that it just rotates around one axis, but it doesn't revolve, contrary to other kinds of wheels that they also change their orientation, such as the centered wheel or the off-centered wheel. The difference here is that the two axes of rotations, they're not intersecting. So we have like an offset basically on the orientation part. And then we also have some slightly more exotic wheels, such as the Omni wheels. Anyone has seen this before? What's the advantage here?
They can slide.
They can slide basically. Yeah, they can rotate and they can also slide sideways, right? I mean, with less effort. These wheels can slide sideways too, but you have to really push it. All right, so they have these rollers which are on the circumference of the wheel. There's typically two of them with a phase difference. So there's constantly at least one of these cylinders in contact with the ground, basically. And yeah, they can slide sideways. And then we have, probably you've seen this as well, what we call the mecanum wheels, which is again with some rollers, but they are placed not perpendicularly, but a bit on an angle. And this gives us some nice possibilities as well. We're not going to go into details on mecanum wheels, but I have this nice video demonstrating, okay, what can we do with them. Basically, by coordinating the rotations of each wheel, we can make the robot move sideways. Here you can see an example, which is pretty useful in certain situations where we don't have enough room to maneuver and so on. So we can move normally like a forward, backwards, like any robot, but they can also move sideways or rotate in place and so on. And there are different options. I'm not going to go through all of them, but just, you know, the idea is that by using these different types of wheels and with different configurations, we can achieve different kind of kinematics. So we'll discuss briefly kinematics of some types of robots. Remind you, kinematics is basically description of pose of the robot. We talked about the end effector when we talk about robot arms. Here we can still call it an end effector. It's basically a frame attached on the base of the robot. As with the drone, we basically have one body that we're moving around, right? And pose, again, reminder, is basically position and orientation. Now, the particularity with mobile robots, with wheel robots, is that we are usually considering just 2D motion, right? We typically consider that robots move on a plane, on the ground, and yeah, we neglect any uphills, downhills, because they're usually like very not steep. Even if they are, we can still consider them, you know, part of a plane, whatever. All right. So the first thing that we'll try to do is describe how, you know, describe a trajectory and figure out how can we move a robot or different kinds of robots so that they follow this kind of trajectory, right? Kinematics. And how we typically do this for mobile robots is that we are transforming a trajectory. Let me show you as well a trajectory. We're transforming these, and we are constantly calculating the curvature at each point of the trajectory, or what we call the instantaneous center of rotation, which is basically the same thing. So we take this kind of trajectory. This is just a line I drew, nothing meaningful, but we calculate at each point what we call the instantaneous center of rotation, which is basically the curvature of the trajectory, because we are going to control the robot based on this property, right? So basically, what is the curvature is the distance to the center of a circle that is tangential at that point of the trajectory. All right. So here I'm trying to demonstrate that. So let's say here the curvature would be basically this distance, okay, which is basically the radius of a circle that is tangential exactly at that point of the trajectory, right? The more steep the trajectory, the smaller the circle, right? The more straight or, you know, less steep the trajectory, the bigger the circle. So here you can see where I take a steep turn, the circle is smaller. Here I didn't draw the circle, but yeah, you can see the distance is bigger. So I will have a bigger circle fitting there, right? And you can see that when I move towards the left, the instantaneous center of rotation is on my left side. When I turn to the right, it's on the right side, right? So where is it if I just move straight? Sorry? Positive or negative? Yes, same thing. All right, no, it's not 0. 0 would be like a circle with 0 radius, a point. So it would be like a, I don't know, a sharp corner basically. That's where the curvature, the radius would be 0. It's at infinity, because for a straight line, the circle that would be tangential to a straight line would be an infinitely big circle. All right? Left or right doesn't matter. It depends where I'm approaching from, whatever the limits. Doesn't matter. All right, so we have to keep this in mind, and we'll try to describe the control for the wheels of the robot so that it follows basically, in order to follow a trajectory, we'll make it follow the instantaneous center of rotations at all times along the trajectory. And the first type of robot that we'll talk, it's the simplest one. It's what we call the differential drive, where basically we have 2 driving wheels. Okay, each wheel can rotate independently, and unless we have some stabilization, whatever, more fancy control, then we need also a third balancing point so that the robot doesn't fall down. It's typically just a roller ball that just keeps the robot from touching the ground, and it can just roll without adding any friction or anything. How is the robot moving? Basically by controlling the relative velocity of the 2 wheels, right? And the assumption is that we have no sliding of the wheels. So we have constant traction with the ground, right? Constant contact. Just to visually show you as well how this looks like, here we have a small video of a robot. So here we have the 2 wheels. And they move independently so that we can achieve different kind of trajectories. Right? So here we see that how it implements basically a circle. Where is this? A circle, and you can see that it's moving like on a nice circle, and it will end up where it started from. I'll fast forward a bit. How can we do a square? Okay. Okay, or how we can do like this infinity shape. So all this is done by the relative velocity between the 2 wheels. I guess you have played with remote controlled cars. It's kind of like, left, right thing. All right, so how do we represent graphically for this course differential drive robot? We have this base here. It has some width. It's basically the width is the distance between the 2 wheels. So this is the left wheel, this is the right wheel, and I have the distance here. The 2 axes have to have the same axis of rotation. Okay. And then I define certain velocities. So I have the angular velocity of the robot, so how fast it's rotating. I have the linear velocity of the robot, how fast it's translating. Then I have the linear velocity at each wheel. See that I produce some linear velocity here and here by rotating the wheels. So I have the angular velocity of each wheel. I have the radius of each wheel, how big are the wheels. And then I have this distance r, which is the distance until the instantaneous curvature, center of rotation, or the instantaneous curvature radius, whatever. Right? So considering I have 2 actuators here, how many degrees of freedom would such a robot have? 2? What do we mean by degrees of freedom.
Translation of X, translation of Y.
But independent.
Just rotation around Z.
Rotation around Z. Okay, so x, y is the plane. And we're moving and z is upwards. Okay, just to have the same names. Okay, so then how many degrees of freedom you say? He says 2. 2 as well?
Yes, because it can translate on unless it's on.
Yeah.
I just
All right. But can I position the robot on a different y?
It can hold the same orientation and the long X and the long Y with the same orientation.
Okay, but it can also, yes. Okay, so it can hold the same orientation and change on x.
Yeah, and also rotating place, so around it.
All right.
Same position, you can change the line.
I'll close the door. So then we have 2. Okay, that's kind of it, and it makes sense to what I kept on saying, you know, like if we have 2 actuators, we have maximum 2 degrees of freedom. The, how do I say, the weird thing sometimes in the logic is that, okay, I can position this robot in a different Y eventually, right, by doing a maneuver. So I can change Y without changing X or orientation. So I could do, I don't know, a motion like this, parking motion, I don't know, and then I changed Y without changing X or theta, correct? But that's not exactly the same thing. I think I mentioned when we're talking about the degrees of freedom for the robot arms, very briefly I mentioned about the holonomic and non-holonomic systems. And basically, up until now, we talked about degrees of freedom mainly in terms of position, but also for the drones and for the mobile robots, we talk about degrees of freedom in terms of velocity, right? So in which directions am I able to change velocity in the end? So for holonomic systems, I can change the velocity in all directions, while non-holonomic systems, I can do it only in some directions. Right, and which means basically that the robot can or cannot move in any direction at any moment, right? Yes, I can change the position of the robot on the y-axis without changing x or the orientation, but I cannot do it, you know, instantaneously by changing its velocity. So I can achieve any pose eventually, but I can do it only through maneuvers. Right, not instantaneously. So that's why we talk about constraints in velocity, not in position. Hi, I just closed the door. So yeah, we have 2 degrees of freedom in that sense, because we can control the velocity forwards and we can change the velocity for orientation, but I cannot change the velocity sideways. Right. Good. Let's describe this pose with some nice letters. So we'll talk about the pose in a world frame, in a fixed frame, earth frame. I think that's why I call it E. So I'll talk about the XY position of one part of the robot, typically the center of the robot. And theta is the angle I have to choose, like a forward direction, and you know, calculate the angle in the earth frame based on that vector, right? And in the earth frame, I will talk about 2 control inputs, basically the velocity, the linear velocity of the robot u, and the angular velocity omega, which is how fast it's going to rotate. All right. Now, if I want to follow a specific trajectory, as I said, we have to calculate the ICR, the instantaneous center of rotation, at each point of the trajectory, right? So if the trajectory has, I don't know, moving along the trajectory, I move along a variable called s, which is the distance on the trajectory. I can calculate basically the curvature or the distance to the instantaneous center of rotation over that trajectory, right? So I call that rs. as a function of s. S is the distance on the trajectory. All right. The idea is that we need to find some kinematics model that tells me how should I move the wheels in order to follow that trajectory, right? That's what would be our basically inverse kinematics. First, we will solve the forward kinematics as typically, so we'll figure out, okay, if I move the wheels a certain way, what would be my instantaneous center of rotation, and then we'll do the inverse. In order to do that, we have to remember this equation that we saw many, many times, which basically tells me how do I convert angular velocity to linear velocity, all right, which is this linear velocity of the wheel will be equal to the angular velocity times the radius. Now, we've seen this quite some times. So yeah, these are all for each wheel, right? And using these, I can basically calculate what would be the resulting linear and angular velocity of the robot for given first of all, linear velocities of the wheels. So let's take this side first, right? So the linear velocity of the robot will be what? The linear velocity of the right wheel plus the left wheel over 2. So it's basically the average or the mean velocity between the two wheels. Right, so let's try to draw something here. So I'll have some, let's say, velocity. Small velocity here, big velocity here. The overall velocity between for the whole robot will be what? Will be the average between these two. It will be basically also geometrically this vector. Okay? Just the average of the two. Again, this linear velocity at the wheel is due to the angular velocity of the wheel times the radius. All right, so that's why from this equation, I can go to this equation. Right, so here UR is omega R times R, and UL is omega L times R. So R gets factored out, R over 2, and the average of the two angular velocities. I assume that the two wheels have the same radius. That's not an assumption. I mean, it's a requirement. They have to have the same radius. Otherwise, it wouldn't be straight. So I can factor out the R, right? Okay. What about the angular velocity? So how fast I'm gonna, so this is U, the omega, as we see there is basically the difference between right and left. So let's call this UR, UL. So it will be this minus this over this distance. This is the width of the robot. Okay? Okay. Clear? Good. Again, I can convert the linear velocities of the wheels to angular velocities of the wheels, because eventually this is what I'm gonna control. Let's try some, special cases. What is the condition so that the robot moves straight without rotating? Sorry? Omega has to be 0?
Yeah.
Which means that, what Antonia said, in order for this to be 0, UR and UL have to be equal, basically, right? So both wheels have to move with the same velocity, right? So if they both move the same, I'm not going to have any rotation. UR equals UL, great. And what's the condition so that I just rotate on the spot without having any velocity? So basically U has to be 0 now, so UR has to be equal to minus UL, right? Which means I have to have this and this, correct? So then the average of the two will be basically 0. Yeah, I didn't do it perfect, but you get it, correct? You also see it from the equation. If these are opposite from each other, u will be 0 and omega will be not 0 unless these are 0. Okay? If these two are equal and non-zero, I will have 0 angular velocity and no non-zero linear velocity. Okay? How do I calculate for any given wheel velocity, how do I calculate what will be the resulting curvature, the resulting radius to the center of rotation? So I want to calculate r as a function of this, let's say ul, ur. How can I do that? Any idea? Use another color. So I want to calculate, where is this? Any idea?
Right. It must be proportional to something. At least you can say that it's proportional to the velocity, right?
Which velocity?
I'm thinking but somehow because direction in the angular velocity it looks like it matters more.
All right, let's see, proportional to the angular velocity. When I have this condition, u equals to 0, omega non-zero, right? So I'm rotating on the spot. Where is the instantaneous center of rotation?
In the center of the road.
So it's here. So r is 0, right? So I have angular velocity, but my r is 0, so it's not exactly proportional, right?
We can do basically in the picture and take the projection of the axis where the wheels are and get a circle that surrounds that axis through the middle of the robot and calculate the radius of the circle.
So,
It's pretty similar with the pure pursuit controller. It uses the same approach. It's taking the projection of the y-axis, that one that's, I think that's the one, yeah. And it's...
let's say this is y, this is x,
Oh, x is there.
if we need it. So we want the projection of what on x?
Of the, not necessarily projection, but the symmetrical of the axis that the robot, that the wheels are staying on.
So, I don't know, think something like this, like the forward direction of the robot.
No. Y-axis then.
So the sideways of the robot.
Yes.
So say if this is x for the robot, this will be y for the robot frame. So you want projection of these on what?
And I think if we're making a circle that's surrounding it, and we're taking the radius of that circle,
Surrounding.
yeah, the start of the robot.
Okay, so let's say I have at any moment I have this circle that the center is here, right? And it's tangential to the robot, let's at this point. Oh, it's intersecting the robot with the center, right? Okay.
The radius of that circle will be the radius.
Yes, but how can I calculate that as a function of these two velocities? That's the question. Or let's take it a bit simpler. How do I calculate this r as a function of these two velocities? The linear and the angular velocity.
If we derive the velocities, we get the position.
It seems so that if the other condition is true, if both wheels have the same velocity, then the radius will be infinite.
Yes.
Okay. And if they differ only a little bit, the radius will be still very big, so it looks like that difference still matters a lot.
Yes, but it feels like it's inverse proportional. I don't know. Yeah. So this angular velocity of the robot will be the same whether I take it rotating from here or from here. So let's try to write it like this. I put this omega here.
Is the linear velocity tangent to the center?
So the linear velocity times,
I asked if the linear velocity vector is tangent to the center.
yes, it is, right? Because the robot moves forward always, and the instantaneous sum of rotation is
If we know u and we know the angular velocity, we can determine the radius.
how?
Using the formula of
Yeah.
Which formula?
Take the formula.
u is w over r.
Exactly. It's the same formula that we used earlier for calculating the linear velocity of the wheel. Exactly. So if I know the linear velocity and I know the angular velocity, I can calculate r or whatever. If I know r and angular velocity, I can calculate whatever. But basically this is the condition, right? And if this is 0 and this is non-zero, r is 0, right? So if I have 0 linear velocity and rotation, r will be 0, correct? Right? R will be here. If this is non-zero and this is 0, meaning straight motion, then this has to be infinite. If this is 0, this is non-zero, this has to be some kind of infinite, so that I end up with a number here, correct? So this is the way I calculate R. So R is basically, oh my god. If this is 0, this is 0. If this is 0, this is infinite. Okay, that's it. Simpler math. So from this equation, we can calculate R as this quantity. I basically take u over omega. So I end up with this part from u, this from omega, and the r's get, sorry, here we don't have the r, so it's L over 2. And if I want to write it with the wheel velocities, the radius of the wheel will get factored out, will get simplified, right? So I can calculate the resulting radius for any wheel velocities. Okay? Good. I can rewrite this in a slightly more elegant format with vectors, with matrices. So I can say u and omega is basically in matrix form like this. And this is the kinematics model in the robot frame, because I'm talking about u and omega in the robot frame, right? If I want to describe this in the earth frame, I have to transfer this u and omega in the earth frame, right? So I'll just put it here because it's not that complicated. So basically I take this vector u and I calculate, the projections on x and y, which is a function of this angle theta, right? So it's cosinus and sinus of theta, x and y. Omega and theta dot, so basically how fast am I rotating in the world frame, is the same whether it's in the robot or the world frame, right? Because it's just one rotation, it's the same one. That's why I have here cosinus and sinus of theta multiplied with u to give me the velocity on the x and the y direction. And theta is basically omega. Theta dot is omega, okay? Nothing complicated. We can also calculate the velocity in the world frame with respect to omega. How can I do that? Because here I have the velocity in the world frame or the earth frame with respect to u and omega.
Just replace u.
Yeah, just place this matrix here, multiply them together. This is 3 by 2, this is 2 by 2, so I will end up again with a 3 by 2. And I will have the relation. I didn't write it here. All right? Good, so this is forward kinematics for a differential drive. What is my resulting velocity? So we talk about velocities, that's why I said earlier, you know, like the whole description, as with the drone, it was velocities that we were talking about, that we're controlling. We're controlling the velocities in the world frame based on the velocities of the wheels. That's our control input. Good. How do we calculate the inverse? I have it already written. How do I get from this to some inverse model? So let's say, and by inverse I mean I have a trajectory Yeah, I can put it already. So I have a trajectory and I have calculated the curvature of the trajectory along the trajectory. Okay, so that's Rs, where S is the distance along the trajectory. How do I calculate the necessary wheel trajectories or wheel velocities over the trajectory so that, you know, the robot follows this trajectory? I basically have, I lost my chalk. I have an Rs equal to this omega, okay, but this is like still the forward. So I need to know omega R and omega L over the trajectory, so I calculate the curvature. I want to do the inverse. Can I just invert this, or what's the problem?
It's not square.
It's not what? Square.
To invert the matrix from before, or just this.
It's not exactly this matrix, because here I don't have R. Okay, I need to have R because that's how I describe my trajectory, right? It's basically just this equation. I have R as a function of left and right wheel velocities. Why I cannot just invert this one?
Because you have multiple results that can be present.
Yes, because I have basically two unknowns, right? Omega left and omega R, and I have one equation. All right, so we have some freedom. We have multiple solutions, and what the solutions, you know, mean is that I have a trajectory, okay, described by the instantaneous M rotation, and my freedom is to choose how fast am I gonna execute it, basically. I can do this slowly, or I can do it fast, right? So that's one of the constraints I can add. I can say, okay, I have a desired linear velocity for the robot, so I can say, okay, I have like UD, U desired. You know, I have a certain velocity, linear velocity that I want the robot to constantly respect. Oops. It doesn't even have to be constant. It can change along the trajectory. I put it as a constant here, so it's not a function of S. But I can, you know, I use the same equation I wrote in the previous slide, and I fix this UD with a specific value. I have Rs that describes my trajectory, so now I have two equations and two unknowns, so I can solve this, no problem, right? It's a linear system, so I can easily invert it, and I can come up with this equation where I say, okay, what's the left and right wheel velocities, the linear ones? As you see, now it's a function of the desired linear velocity and of the curvature, right? Or I can write this as the angular velocities of the wheels. It's nothing complicated, right? I just divide by the wheel radius. Okay? So that's basically inverse kinematics for a differential drive. Again, this assumes we have no slipping, which means I can constantly calculate, you know, where the robot will be by calculating the velocities of the wheels or how much they rotate it. We'll see a little bit what we can do if we have slipping later on, but yeah. Everything clear here? Differential drive? Great. The next type of robot that we'll see is what we call the tricycle. Basically, it's a robot with 3 wheels. It has 2 fixed wheels with the same axis in the back. or it can be considered the front, but yeah, typically this is the back side. The two wheels can move independently, but they're not actuated. Okay, they're just passive, like the rear wheels of most cars, where they're just, the front wheels are driving and the rear wheels are just rotating. All right. And there is one wheel in the front that is steering, and it's also, there is traction, so it's also pushing the robot, or pulling. Typically the third wheel is in between the other two, and it has an offset like it's more in front. How does this look like? The steering wheel here is on this side, on the left side. I don't know what's front and back, doesn't matter. I'll turn off the music. You get the idea, right? All right. Again, we talk about the location of the ICR. So the point is to figure out, based on these control variables, the steering angle, alpha, and the angular velocity of the wheel, to calculate again the linear angular velocity of the robot and the position of the instantaneous center of rotation. All right. So this typically looks like this. One thing that I didn't mention about the instantaneous center of rotation, because it was not so relevant for the differential drive, but this center of rotation will always be along the axis of the wheel rotations, of the axis of rotation of all the wheels, right? So it will always be on top of this line, because I have this is the axis of rotation for the rear wheels, right? And then it will always be on the axis of rotation of the front wheel as well, right? So here you can see if I steer to the left, I will have this perpendicular line, which is the axis of rotation of the front wheel, and it will intersect somewhere this line, the axis of rotation of the rear wheels, and the position of the instantaneous center of rotation will be at the intersection of the two, right? If I steer to the left, to the right, then it will be on the right side. Yes?
This means that the different robots that have different length, the D there,
Yes?
will move differently, even if their front will behave the same.
Yes.
And
Slightly different.
So this means that it's the tricycle robot. It's not the same as if there would be two stabilizing like roller coasters instead of this.
The same as the differential drive, you mean?
No, I mean if I have this robot from the table and another one, but instead of the wheels I put something that are not something just to stabilize it and as low friction.
Like roller balls, yes. Yeah, it wouldn't be the same, because the roller balls can rotate around any direction, right?
Okay.
So then you don't have a constant axis of rotation. So then you don't know where the instantaneous center of rotation will be.
Yeah, okay. The physics part I was asking, the mechanics.
Isn't it kind of the same thing? I don't know why the physics is different from what I'm saying.
No, I understand.
Okay. Yeah. So if here we didn't have like a fixed axis of rotation for the real stabilizing parts, then we wouldn't be able to predict where the instantaneous center of rotation will be. Okay. And you can imagine, having two roller balls in the back. I don't know, me at least, when I imagine it, I see a robot just sliding randomly. Anyway, the explanation is this. Yeah, the instantaneous center of rotation will always be on the axis of rotation of all the wheels. All right? Because the rear wheels are not steering, it will always be on that line. And yeah, the instantaneous center of rotation will always be determined only by this angle in the end. Right? Can we calculate this distance, where it will be? Based on the angle alpha. Basically I have this triangle. Okay. This is alpha. And then I know this distance d. And I want to know what is r.
Vertical angle of the 90 minus alpha.
90 minus alpha will be this one, right? because this is perpendicular. This is 90 degrees, right? We said the axis of rotation of the wheel is perpendicular to the wheel, right? So this is pi minus alpha.
And the other one is pi over 2, so we know that...
Which one is pi over 2? This one? This one? So this is?
Actually, I was thinking that the angle, like opposite to the vertical line is alpha.
This one?
It's pi over 2.
This is alpha.
And then
Yeah, it's alpha. All right, this is 90, so this is pi over minus alpha.
Pi over 2 minus.
Details.
Yes, and this
Alpha is-
log science.
And this is alpha. Because this is pi over 2 as well. All right, so how much is R? If I know alpha and I know D,
And we also know the other angle, so we just know the log sine. So d over alpha is pi minus 2 minus alpha divided by alpha. Or the opposite, actually.
D over alpha, R, or what do you say?
D over alpha.
D is a distance, alpha is an angle.
Yes, yes. No, it was right.
Okay, D over R is?
It is the opposite, alpha divided by pi minus over.
Tangent of alpha, right? I don't need to know this. I know the angle, I know D, I can calculate R. So it's tangent of alpha. Great. So R will be basically D over tan of alpha. All right. Let's prove it a little bit. If alpha is 0, tangent is of 0 is 0, D over 0, infinite. So R is at infinity. If A is alpha, A is 0, it's looking straight. I will be going straight, so curvature at infinity. If A is 90, extreme case, right? If A is 90, tangent of 90, infinite, D over infinite, R will be 0. Don't tell this to mathematicians, they will kill me, but yeah, anyway, whatever. Approaching to 0. But you can imagine if this tilts 90 degrees, then I will rotate around this point. So R will be 0. Just a quick validation. Right, and we see that the location of the instantaneous center of rotation depends only on the steering angle, not on the velocity. Right? Which makes some sense. Good. What would be the angular velocity? So how fast I'm rotating around this point. Sorry? The angular velocity of the driving wheel, which will result in some linear velocity of the driving wheel, UW, and I need this distance, right? Because then I have again the same equation, like UW will be omega times this, I don't know how to call it, hash. Hypotenuse. How much is this? Sorry? Or from alpha, I can choose different ways. Let's see how did I write it here. Yeah, I took it as D sinus alpha, or sinus alpha over D. So I know has is, no, has times sinus of alpha is D, correct? So has is D over sinus alpha. So I can put d over sinus alpha here, and I have the same. Is the same?
Yes.
D over sinus alpha, yeah, and then when I move it, it's sinus alpha over d. What I have there. Or what I did here is also Pythagoras, basically. It's another way. So r squared d squared square root, and I have this has. Okay. And what will be the linear velocity of the robot? The linear velocity will be basically in the frame of the robot, right? So it will be this vector here. It will be the linear velocity of the wheel, projection on this axis, cosinus of alpha. Okay? So in the end I have these three equations. So this is now my forward kinematics model. I can calculate linear and angular velocity of the robot based on the steering angle and wheel velocity, and also the instantaneous center of rotation. How do I invert this one? To calculate the inverse. So what if I know a trajectory, which means I know r over the trajectory, how do I calculate the wheel velocities and steering angle?
We fix one parameter again, no? Let's say yes.
We kind of have to, yes, in a way.
We fix the velocity and we only control it, because it looks like the cars do this, so we might as well.
Yes, but basically you see it from the last equation as well. I can solve for alpha without any dependency on the velocity, because we said curvature will only depend on the steering angle, right? So I can take the last equation, invert it very easily, right? And then I can choose one of the two. I can say, okay, I want to transverse the trajectory with a given velocity, linear velocity or angular velocity. So I can fix the, or I don't even have to fix the linear velocity. I can have like a varying velocity along the trajectory. But point is that these two equations are kind of independent. I can solve alpha just based on curvature, the steering angle based on curvature, and then I choose one of the other two. I know alpha now, and I can choose the wheel velocity based on the linear velocity or angular velocity I want to execute the trajectory from. All right? Simple. You see, these forward inverse kinematics for mobile robots are a bit simpler than for robot arms. Let's see how do we describe things in the world frame. It's kind of the same thing as for the differential drive. Here I didn't put it, but I have a linear velocity vector here. Oops. And an angular velocity omega. Very ugly. And I can just take this vector, calculate the projections on x and y of the earth frame, which again multiply just with cosinus and sinus of theta, the angle of the orientation. And yeah, the angular velocity on the world frame will be the same as the angular velocity on the robot frame. So theta dot equals to omega capital, this should be. Okay? I can calculate the inverse in the world frame as well if I want. I basically just invert these equations. Whatever, not going into too much detail here. Shall we take a break before going to four wheels? It's not a big jump, but it's 3 o'clock, so let's take a break.